so far we have done what? We have done one variable hypothesis testing, and then goodness of fit, meaning testing of the underlying distribution itself whether it is normal or not, and the other assumption we kept on making is test of independence, IID, we always said independence, right. And not only that, many a times you wanted to do whether two variables are independent or not, sum of n random variables, n independent random variables. The assumption of independence is a key in your central limit theorem, and in many a times independency is something which we want to test. Remember, if you want to take, if you give me a let us say if I ask you to extract features from a image, that will help you distinguish, classify the image, okay, and you are restricted in choosing the features. How will you go about choosing the features? So let us say you want to choose very minimum features, but with the minimum features you should be able to classify. What kind of features will you go for? In other words, so let me take a simple example. This may be, if I give this example and say f1 plus f2 equals to f3, I have this equation. Now I am saying I want to store minimal amount of data. So let us say this is from sensor, 1000 data points, 1000 data points, 1000 data points, right. If my storage space is limited, how do you go about storing this? If my storage space is limited, most often do not think we have infinite storage, today there is infinite amount of data as well. How do I limit my storage? How do I store efficiently? Will I store all these 3 variables? How many variables are required to store? 2 variables. If I know 2 variables, I can compute the third one, because this equation is known. If I know this equation, it requires only 2. So what is that number? 2 independent variables. If I store f1 and f2, f3 is automatically dependent. So independency is a very important property, whether in your feature extraction, whether in data storage, or whether in further processing, whether in how do I use these relationships, etc. Is there any relationships, modeling, this independency is a very very important concept. And what we are going to learn is test for independency, okay, that is also called contingency table, okay. So many a times the n elements of a sample from a population may be classified according to 2 different criteria. We are only doing 2, we will extend it to n later on, okay. For this right now I am doing only whether 2 variables are independent or not. Of course you can compare against, do this test for multiple variables in pairwise, then you can do independency test. So what is my question? Many a times sample from a population may be classified according to 2 criterions, and I am asking whether the 2, it is of then interest to know whether the 2 methods of classification are statistically independent, that is these 2 parameters are statistically independent or not. Suppose you have feature 1 and feature C1 and feature C2, you classify using feature C1, you classify using feature C2. You want to know whether these 2 methods are independent or not, that means you want to know whether C1 and C2 are independent or dependent. Methods of classification, for example, we may consider the population of graduate engineers and whether the starting salary is independent of academic disciplines. So now starting salary is my one variable and academic discipline is my another variable. Taken from independence IID population pa. If x1 to xn are samples, n samples, take from IID population, not of the sample. Observations is always assumed to be random. Observation most of the time we assume it to be random unless it is a time series. Population itself is IID, that is what CLT's assumption is, and in case of T distribution the population itself is normal. So you are only assuming about population. When you want to determine sampling distribution of x bar, your assumption will be on the population, not on the sample itself.
So here we are not testing if observations are independent.
No, it is about the variables, it is about the underlying variables are independent or not. How will I test this? By taking samples, that is a different story. but the inference is about the population. Remember, always inference is about population. In sample, what is there to infer? You give me 20 samples, I will say whether they are related or not simply by taking the values, but that is not what I want to infer. I always want to infer about the population. Here inference is always about population. So we have two methods, because basically there are two variables of interest and we want to know whether they are independent or not. So two methods and two variables. So we have, let us say, rows and columns, because this is a matrix now. Okay, so we have rows as one of the variables and columns as the other ones, and we construct what is called as a contingency table, which is an R cross C contingency table. Okay, so assume that the first method has, or the first variable has R levels and the second method has C levels. Okay, Oij is the observed frequency for level I and J, for first classification and J on the second classification. So Oij, ith level first variable and jth level second variable. So let us say salary $60,000 or 1 lakh rupees, biomedical engineer, starting pay per month, and this is one, and then you have multiple levels. Let us say we are the highest, we get 5 lakhs per or 10 lakhs per month, and then we start from 1 lakh for others. Let's, which department you hate? Let us say computer science, coding, you are all not happy with it. So we have computer science to be the lowest and biomedical to be the highest, multiple levels, and then you have what, academic, and then so salary is, and then academic engineering, so biomedical, electrical, civil, mechanical, etc., and then salary range in the other axis. Then you want to see whether the salary is independent of the academic discipline. Is that true? So you do not have an answer, right? Maybe, may not be, you do not know the answer, right? So that is what data has to reveal, that is what we want to do. Okay. So let us construct this table and then do it. Okay. So this is the table I have. Okay. So we have pension plan and job classification. There are 3 pension plans and there are job classifications. We want to know which pension plan which worker has opted, right. So very high plan, will a normal salaried worker will opt? Most likely no. So there may be a relation between the pension plan and the job classification itself. So we have 3 in both the ends and data is given to you. This is my observed data. Okay, this is my observed data. Okay, and now I want to verify whether they are independent or dependent. That is a question, right? My data is given to you, the data is given to you, one level, for one variable there are levels, R levels, the other variable there are C levels, it is an R cross C table. This table is given to you. With this table I want to know whether these two variables, the pension plan and job classification, are independent or dependent. That is what I want. So how do I go about, what is the idea behind independency? When two variables are independent, what do I have? What do I have when two variables are independent? Probability of A intersection B equals to probability of A into expectation of xy equals to expectation of x into expectation of y. I do not care about there is no relationship. Probability, the fundamental, I showed you how to do probability of A intersection B, right. Probability of A intersection B equals to probability of A into B, probability of, we derived it in the class, right. The moment you understand that, then expectation of x y is nothing but expectation of x into expectation of y, right. So that is the concept we are going to do. Okay. So now we want to know the expected values, then they are independent. These are my observed, what is expected value in each cell. So this is my observed values, I want to know the expected values, these values in each cell. How do I go about it? So to find the of the expected values, no, we assume that all the values, we assume what is our null hypothesis, all are independent. So now assuming independence, the estimator, so let us define some variables, okay. So let me complete, let us define some variables, let Pij, so these are some jargon, I mean definitions I am going to use, let Pij be the probability that a randomly selected elements falls in the ijth cell. Let Pij be the probability that a randomly selected one falls in the ijth cell, okay. Given the two classes are independent, what is Pij? What should be Pij? P of I into P of j, that is row into column, row probability into column, that is what I have written at ui into Vj, okay. Instead of Pi into Pj I have written it as ui into Vj. Ui is the probability for the row and Vj is the probability for that particular, assuming they are independent. So what is ui? Ui is the probability that a randomly selected elements fall in a row class I, and Vj is the probability that randomly selected element falls in the column class j. What is ui hat? I want to know ui hat, ui, that is ui hat. What is a good estimator of ui hat? 1 over n times summation j equals to 1 to c Oij. What is it? You sum along y axis or j axis, you sum for along j axis, you get the probability for particular I, you sum along I axis, you get the estimator for j. So now I have an estimator for u and j. Then what is my accepted expectation? Expectation is equals to n p, right, n Pij, that is my expectation. Now assuming they are independent, this should be n ui into Vj, and I have the estimate of it, so that should be equal to n ui hat into Vj hat, clear, right. Ideally expectation is n Pij, I have assumed that the underlying population is independent, so Pij should be equals to Pi into Pj or ui into Vj. Ui estimate is ui hat, which is based on observation summed along the jth axis, and Vj hat is the observation probability obtained summing along the ith axis. So we have ui hat into Vj hat, okay. Now if you go back to this problem, so now once I have the observed and the expectation, I am going to do the chi-square test, that is all I am going to do, summing along both the axes. It is 2 dimension, so I will sum along both the axes, and instead of n minus 1 degrees I will have r minus 1 into c minus 1 degrees, okay, because it is 2 dimension, 1 dimension, so I will have 2 summations and n minus 1 into c minus 1 degrees of freedom, okay. But the key point is, now this is my observation, how do I get the expected? Can you calculate the expected for this problem? Can we calculate the expected for this problem? Please do it. The problem statement is given, if you do not understand please let me know. So we have to compute u1 hat, u2 hat, u3 hat, and similarly v1 hat, v2 hat, v3 hat, right. So how do you compute u1 hat? 1 over n, u1 hat is nothing but 1 over n summation j equals to 1 to c Oij for that particular row, for that particular row. So what is that first row? 160 plus 140 plus 40, 340 divided by n is 500. So u1 hat is 0.68, u2 hat is what? 40 plus 60 plus 60, 160 divided by 500, that is my u2 hat. Similarly what is v1 hat? v1 hat is 200 divided by 500, v2 hat is 200 by 500, and v3 hat is 100 by 500, clear. So now these are my things, and then what is expectation of 1 comma 1? u1 hat into v1 hat into n, so that is how I get 136. So I can do this for the second u2 n, u2 hat, v2 hat. What is that? That is this diagonal 2 comma 2, 2 comma 2 is here, this is not a diagonal matrix. 2 comma 2, what is the answer? 500 into what is u2 hat? u2 hat is 0.32 into v2 hat is 0.4, that is what we have. 500 into 0.4 200 into 0.32, that is what I have. 200 into 0.22 is like roughly 200 by 3, 1/3 of 200, which is like 64, that is what I have. Okay. So you can compute the expected frequencies. This is the table you have to compute, assuming the table is constructed assuming that rows and columns are independent. Now this is the observation, this is my expectation if they are independent. Now once I have that, all I have to do is the test statistic, which is nothing but observed minus expected the whole square by expected, and this is 2 dimensions, so it is summed along both I and j axis, right, and the degrees of freedom is given by r minus 1 into c minus 1. Okay. So I have chi square calculated, and then chi square computation is 49.63, and since 49.63 is greater than chi square of 0.05 comma 2, we reject the hypothesis, null hypothesis, because obviously by starting only we should know salaries and pension plan will be related. That is what the data is also revealing, that they are not independent. So this is for test of independency of 2 variables. This also can be done for what? Continuous variables. This I have shown it for discrete, you can also do it for continuous variables. Clear? This is the way statistically, whether you want to say how much percentage whether you are confident whether it is independent or not independent. Make sense?